All right, today we begin the section, or I should say the next section dealing with electrons, and that is pertaining to dot diagrams. And from prior knowledge, you perhaps remember from physical science, there's both covalent and ionic types of bonds, and that's what this chapter deals with. We just put this all together in one unit, if you want to say, these dot diagrams along with configurations and the Bohr models and the quantum numbers. We just put them all together. So this is actually in chapter 6, and that actually starts around page 180, actually 174 is where that begins. And perhaps just to help you out, on page 184, where there's, it's actually figure 10, it's illustrating these electron dot notations, and where you see this table says number of valence electrons, it just goes 1 through 8 that we see, and the next column over says electron dot notation, which means if there's a 1, it just would get 1 dot, of course, and then an example would be your alkali metals that you would see with sodium, potassium, I think is rubidium, yes, cesium, francium, lithium, of course, and then hydrogen is the exception. Even though it's a gas, it still has just 1 valence electron because it's in column 1. That's one of the, what I want to say, concepts that we wanted you to understand when utilizing that periodic table, is that when we see this, that's why the S and P blocks is utilized in this notation. We skip the D blocks when it comes to that of electron, the valence electrons. We still use them as far as, this would be an example. For instance, we know like iron chloride would certainly exist. It's not that we skip over them, this having a -1 that has a +3. And again, the reason that we don't want to introduce these transition metals yet is because wait till I'm here for one and can explain that in person. But if you remember from physical science, what we would want to make sure you understood for these concepts is these are your first 2 columns in S block and your last 6 there in the P block. And that's why we also refer to that as, of course, an octet rule. Okay? That each electron, or not each electron, each atom is trying to get 8 electrons within its outer energy level. And everything that we would have done up to this point would certainly illustrate this. And for some of us, it might be just be a quick, what I want to say, refresher course, or perhaps a stroll down memory lane if you want to look at like that, or a reminder. That maybe that's the best way to look at it. Okay, so a lot of this is, again, just based off of old knowledge, and that would probably be, this would be your best example, that potassium bromide. But there again, on figure 10, as you go down, number of valence electrons, if there's 2, it's an element in column 2. Those are your alkali metals. Remember, alkaline earth metals are in column 1. And then you skip all the way over to 3. That's why we made that iron chloride notation. You start here, alkaline earth, alkali metals. We skip them and go all the way over here to boron. That's in column 3, all the way up to column 8 then. That's where you see, of course, boron, carbon, nitrogen, column 5, oxygen, column 6, fluorine in column 7, and neon there in column 8. And one of the aspects that we do when we're looking at this is, of course, we don't put hydrogen on there, or excuse me, helium on there, because that is, of course, an exception to the octet rule, because even though it's in column 8, okay, it only has 2 protons, so therefore it could only ever have 2 electrons, making that a very stable compound. Okay. So when we do this, it says electron dot notation. We're really familiar with that. On the page next to that, on page 185, It says these representations are all Lewis structures, okay? Whether you decide to do one like this, okay? This is the simplest and most stable bond that there is between hydrogen because they're both in column 1. That's one way to represent it, or you could illustrate it like this. It means the exact same thing. You're just turning these sideways. Here's your one electron from this hydrogen, and then the triangle would be from this hydrogen, therefore making that bond. When we're talking about Lewis structures, it means both of them you could say at the same time, or making reference either using dots or using dashes. Okay. So, as you would guess, we just want to take a quick look at this on page 185, where it talks about these Lewis structures. Maybe we should read that together. It's about halfway down. These representations are all Lewis structures, what we just showed you with that hydrogen atom. Formulas in which atomic symbols represent nuclei and inner shell electrons, dot pairs or dashes between two atomic symbols represent electron pairs and covalent bonds, and dots adjacent to only one atomic symbol represent unshared electrons. Okay, it is common to write Lewis structures that show only the electrons that are shared using dashes to represent the bonds. The structural formula indicates the kind of number, arrangement, and bonds, but not the unshared pairs of atoms in a molecule. For example, you see F-F and H-Cl are structural formulas. The Lewis structures, and therefore the structural formulas for any molecules, can be drawn if one knows the composition of the molecule and which atoms are bonded to each other. The following sample problem illustrates the basic steps for writing Lewis structures. The molecule described in this problem contains bonds with single shared electron pairs and single covalent bonds, or a single bond is a covalent bond in which one pair of electrons is shared between two atoms. Okay. And when you're doing these on page 186, what it's actually trying to illustrate is trying to determine how many electrons you should have total. But as long as you are using your periodic table properly, you'll never be misguided by that, because you're always using the electrons in the outer energy level. Okay, so let's perhaps go through and do some of these examples. Okay, so this would be very similar. The first example they have is CH3I. Okay, it's just a coincidence. We wrote this one up here. So carbon, of course, is in column 4. Hydrogen's in column 1, and then chlorine's in column 7. Okay, then you have to look at these little subscripts, of course, so that we know we've got 4 from the carbon plus 7 from the chlorine, and then plus 3 is 14. Okay, so as long as you're always just dealing with your valence electrons, we should be just fine. And that's how we taught you that 2 years ago in physical science. So to do these, typically when carbon is present, that's always going to go in the middle. And typically when metals are present, you probably want to put those in the middle. So here we go. Here we see carbon being in column 4. So just go ahead and put those 4 X's, denoting those 4 valence electrons. Okay. Looks like that's fading a little bit, so let me just grab a new marker here. Then everywhere that we see a dot, that's where we're going to form a bond. Here we have a hydrogen. Just go ahead and put a triangle. Of course, if you remember, you can use dots, X's, triangles, E's, anything that you would like to illustrate that. Okay, so we got 2, 4, 6, 8, 10, 12, 14. Like we looked at earlier, And when it comes to this octet rule, okay, metals do not want 8 electrons around them. And of course, even though hydrogen's not a metal, okay, it doesn't want 8 electrons around it either because it only has 1 to give away. Okay, then this is optional. You can always put boxes around there to illustrate, okay, does each one of those have 8 electrons? And of course, those do. Again, these have metallic-like characteristics. That's why hydrogen does not have 8 around it. It only has 1 electron to give away. Okay, then the next molecule, it's actually a molecule, is the next one we see, with that of chlorine. And that can be illustrated. And we had introduced this last section or chapter, if you want to call it that. These bonds are based off of this content here. Okay, so you have 1s, okay, 2s, and then 2p. Okay, then 3s, and then here's our 3p. Okay, so that's for one atom of chlorine. And notice, again, we want electrons in the outer energy level, and that would be these. And it's probably a little more clear to see from the Bohr model how all this actually ties together. Okay, we know we've got 17 in the middle, 1s2, 2s2, 2p6, 3s2, and then 3p5. Okay, so here we've got these 2 electrons are represented right here, and then we've got these 5 represented right here. So all together that gives you 7, and that's why chlorine, of course, is in the 7th column. So maybe it's a little more clearer to see these electrons from that Bohr model. So that is one chlorine atom. And then we can do a second one underneath it, of course. Okay, so when these overlap, what it's actually trying to illustrate on, is that page 183, I believe? Yes, okay. They use fluorine atoms, but the characteristics would be just the same. Is that when we look at this box right here, okay, that's where that bond forms, okay? So when these overlap, that just becomes more stable once those two come together to make a bond right here. Okay, so what that means then is as follows. Okay, chlorine being in column 7. Okay, and then we're going to put one right next to it. So then this right here is being shown by right here. And that's where that concept comes from. That's where that bond forms, because these two overlap one another, and therefore this electron gets shared in between these two. That's why you see 8 electrons around each one of them now, therefore satisfying that octet rule. Okay. But again, all of this is from prior knowledge that we've done before, and we started with the Bohr model, then we did these electron configurations, and now we're putting these together to illustrate bonding between atoms. Okay, so we can get rid of this content here. we did the hydrogen atom already, so let's go ahead and do KBr, or potassium bromide. We'll just go ahead and start with our bromine. And again, that's a halogen in column 7, so therefore we know we can go ahead and put 7 electrons around there. It wants one more, so it gets that from the potassium, and therefore there's our bond, potassium bromide. Nothing around the potassium, all of the electrons around the bromine. Again, this is just optional if you choose to do that. You don't have to put those boxes around there. Then finally, we move ahead to the phosphoric acid or hydrogen phosphate. Okay. And in this case, how would you know which one to start with? That would be the element with the least number of subscripts. So in this case, it would be phosphorus. That would be where you would want to start with that. And when we do that, okay, it branches out in all directions. Okay, think about where phosphorus is. That was part of your homecoming Olympics for some of you who had participated in solving that puzzle here in this class. This being in column 5, as you would guess. Okay, 1, 2, 3, 4, and 5. So that takes care of our phosphorus. Then we'll just, everywhere that there's an X, we want to create a bond. Then think about what column, where's oxygen located? Of course, that's column 6. So we got 3, 4, 5, and 6. Takes care of one oxygen. We'll go ahead and do another one. Okay, and then move right around the corner here. Okay, and then this looks perhaps a little different, okay, just because here we're illustrating a bond between here. Here we're going to illustrate where these electrons, these 2 electrons are being shared with this oxygen. Okay, and then as we look at that, you might notice that we are 1 electron short in 3 of our oxygen atoms, because this one has 8, 6 from its own outer energy level is sharing these 2 with this phosphorus. That gives that oxygen 8. Okay. Then here we have a single bond between this phosphorus and this oxygen. It's 1 short, but notice we still have these 3 hydrogens left, so we can add a hydrogen here, a hydrogen down here, then a hydrogen over there. And therefore now we know that each one of these has to be satisfied because the phosphorus has 8 around it and each one of those oxygens has 8 around it. And if you wanted to, we know that 8 times 4 is 32. Okay, and then, well, it's 32 of course, but what I meant to say, column 6 times 4, we got 24. Okay, plus 5, okay, and plus 3 more. Okay, so 8, that gives you 32. Okay, I was thinking about the end result in getting to that number of 32. Of course, there are 8, 8, 8, and 8. Okay, of course, you take that times 4 would give you 32. Of course, this isn't necessary either. It just perhaps helps you to maybe illustrate how many electrons there's supposed to be and how many electrons you actually have, because when we get to covalent bonds, that gets to be perhaps a little more tricky. Okay. So we will continue with this tomorrow. I do believe it says on the board, sign a paper on Tuesday, so we'll hopefully be ready for that. Okay, so that's all I have. We will catch up to you next time.